Hi everyone, this is Aditya Goyal, Aditya Mishra and Aditya Kumar, and we will be providing you solutions to the problem set 2. I will be explaining both the problems. He will be giving the solution of the problem 1 and he will be giving the solution of the problem 2. Thank you.
Problem statement 1. An industrial monitoring system fails its safety checks because the calibration module expects sensor readings in IEEE 754 single precision hexadecimal format, but the conversion circuit has malfunctioned. Two critical measurements must be manually converted: minus 85.125 absolute zero temperature and 5 by 6 pressure coefficient to the correct IEEE 754 single precision hexadecimal representation. To complete the calibration process, convert each value to IEEE 754 single precision hexadecimal format to restore the safety monitoring. So what we have to do is we have these two numbers and we have to convert them into IEEE 754 single precision hexadecimal format. Now what exactly is this? I will tell you in the next slide. So IEEE 754 single precision floating point format is a set of 32 binary digits 0 or 1 which together make a floating point number. For this, the first bit is the sign bit, the next 8 bits are the exponent bits, and the next 23 bits are the mantissa bits. The general format is plus minus 1 point mantissa in the base of 2 multiplied by 2 to the power exponent. Now here, where the sign is positive, we take it as 0, and whereas the sign is negative, we take the first bit as 1. This M here will represent the mantissa and this exponent here will represent the 8 bits exponent in the above format. Now we have to keep in mind that the exponent that we represent here in the 8 bits is biased. So whatever we get in this form, we will add 127 to it to add in the actual representation where the 32 bits are present.
So now coming to the solution of problem 1. In problem 1 we are given the number minus 85.125. First we will ignore the sign and focus on the main part. 85.125 can be written as 85 plus 0.125. Now 85 is written in binary as 1010101 and 0.125 as 0.001. We will combine them to get 1010101.001. According to the general format of floating point integers, we have to take only one point some decimal part into 2 power something format. So we will convert it into that format. So we will get 1.010101001 into 2 power 6. Here this part is the mantissa of our format and 6 is the exponent. To bias it, we will add 127 to it. So we get 133. Here the sign is negative, so we will get MSB as 1. Therefore we get MSB is equal to 1, exponent is equal to 133, which is represented as 100000101, and mantissa as 01010101, followed by 14 zeros because we have to complete 23 bits. So now combining them in the IEEE standard format, we get in binary we get 110000101 and the mantissa as 0101011001 and then 14 zeros. Now combining them in the group of 4, we can convert it into hex codes. So we will group them in 4 as like this. Now here are 8 hexadecimal digits. So the hex code for -85.125 will become, the first 4 digits will be OXC, the next 4 digits will be 2, the next 4 digits will be A, and the next 4 digits also will be A. Then we have next 4 digits as 0100, which is converted as 4, and the last 3 digits are zeros. Therefore, we have this number as the IEEE 754 standard single precision format of -85.125. So now moving to the second part. The second part is 5 by 6. Now 5 by 6 can be broken down as 1 by 2 plus 1 by 3. Now using some mathematical approximations, we can write down 1 by 3 as 1 by 4 plus 1 by 16 plus 1 by 32, 1 by 64 plus, and so on, and it will go to till 0. So now we will write 1 by 2 as 0.1, 1 by 4 as 0.01, 1 by 16 as 0.0001, and so on. It will continue. Combining them will get 0.11, 01, 0, 01, 01, and so on. It will continue till infinity digits. But according to the general format for floating points, we will convert it as 1.101010 and so on into 2 power minus 1. Now here this part is the mantissa and this is the exponent. Adding 127 to bias it will get 126. Now 126 is represented as 0111110 in binary. Therefore we have the MSB as 0 because the sign is positive, and exponent as 0111110, and the mantissa as 101010 continued to 23 bits, which will end in 1. So combining them in IEEE standard format for binary, we get binary representation as 0 0111 1110, and the mantissa 1010 1010 1010 1010, so on, followed till 23 digits. Now grouping them in group of 4s, we will get like this. Converting them in the hex format, we will get 0011 is 3, 1111 is F, 0101 is 5, 0101 is again 5, and all the remaining digits are also 0101. So we will have 4 more 5s in a row. Therefore, the hex representation of 5 by 6 is 0x3f555555. So this is the required representation of 5 by 6 in IEEE format.
Problem statement 2. A processor has 32-bit instructions with 256 registers. Complex instructions need 3 registers. Simple instructions need 2 registers and a 10-bit immediate value. Control instructions need 1 register and a 12-bit address. Memory instructions need 2 registers and a 6-bit displacement. With 32 complex instructions, 16 simple instructions and 64 control instructions, find the maximum number of memory instructions. Now this question is of instruction encoding, about which I'll tell you in the next slide. Instruction encoding is the process of translating higher level computer instructions into a specific binary format that a processor can understand and execute. Now this binary format contains three parts: the addressing mode, the opcode, and the operand. The addressing mode is what kind of instruction it is. For example, it can be a complex instruction, and the opcode is the number of instructions in that addressing mode. For example, a complex instruction can have 32 opcode, 32 instructions which will be seen by the opcode, and the operand is the registers we are using for that encoding.
Now coming to the solution for problem number 2. So some information given in the question is that there are 32 bits instruction length and 256 registers are present. So now 256 is 2 power 8, so it will require 8 bits. Now we have been given these 4 instructions: complex instructions, simple instructions, control instructions, and memory instructions. So let's now consider the encoding for all of them. So for control instructions, we have 32 instructions, so they will require 5 bits, as 32 is 2 power 5. And there are 3 register operands. Let's call them R1, R2, R3, and each one will be of 8 bits. Now these 5 bits here will represent which complex instruction it is, and so we are left with 3 bits. Now coming to simple instructions, there are 16 simple instructions, which means there will be 4 bits required, as 16 is 2 power 4, and there is also a 10-bit immediate value. So taking this into consideration, this is the 10-bit immediate value, and there are 2 register operands, so R1 and R2, each of 8 bits, and this 4-bit for simple instructions. So after all of this, we are left with 2 bits. Now coming to control instructions. So there are 64 control instructions, so they will require 6 bits, as 64 is 2 power 6. Also a 12-bit address is also present. So let us write the address here. So it will be of 12 bits. There is also one register operand, R1, let's say, of 8 bits, and this 6 bits for control instructions. After all of this, we will be left with 6 more bits. Now coming to the memory instructions. So there is a 6-bit displacement here, along with two register operands, so after all of this, we will be having 10 bits remaining. So now we will try to find what is the maximum number of memory instructions in this encoding scheme. So let us address the control instructions as a string of 6 zeros, the complex instructions as 2 zeros followed by 1, and simple instructions as 0, 1. So the options left for memory instructions are as follows: 5 zeros followed by 1, and then 4 bits, which could be either 0 or 1, or there could be 4 zeros followed by 1 and then 5 bits remaining, or 3 zeros followed by 1 with 6 bits remaining, and all rest of the one starting with 0 are basically covered here, like 201 will represent the complex instructions, and a single 01 will represent the simple instructions, and all 0 will represent the control instructions. So now if the first bit is 1, then we make sure that it is a memory instructions. So there will be 9 bits left for this. So in this case, the 4 bits left will take 16 unique values. Here 5 bits left will take 32 unique values. Here the 6 bits left will take 64 unique values, and here the 9 bits left will take 512 values. So in total, the maximum memory instructions which could be encoded in this scheme will be 512 plus 64 plus 32 plus 16, which will come out to be 624.